Hi, today we're going to look at how to evaluate models, specifically how to tell if the model is going to generalize to data that we have not seen yet. We're going to look at a phenomenon called overfitting and how to use the technique called cross-validation to prevent that from happening. In any classification problem, what we want to do is for the model to generalize to data that we have not seen. So that means when we build a model using known or seen data, then we want the same model to work well for unknown or unseen data. In other words, when we train or build a model, we want to know how to turn the knobs or the parameters in the model so that it can work really well for the training data, which is another word for seen or known data, where we train the model or to build the model using those seen or known data. And we want the same model to work really well for the test data, which is another word for unseen or unknown data. And training data and test data, or just the word train and test in general, is a very common terminology that you're going to hear a lot. So you may ask, so why do we really need to distinguish between training and test data? It seems like that if I can get a very good model that works well for the training data, then it should ideally also work really well for the test or unknown data. So the main reason is that it's actually very easy to have perfect classification on the training data. So that means you can actually build a perfect classification model that can have 100% accuracy. Why can it work so well, and what's the problem with that? So the reason we can do it is because you can imagine you can write millions of rules, and that will allow you to zero in to this very specific data point in your training data set. So that means ideally you can just remember all the rules and then also remember the label. So next time you see another data point that's exactly like your training data point, then you can just recall. It's essentially like looking up the labels. However, these millions of rules that you've written, they may actually not generalize to the test data. So meaning you may have so many rules, actually you may not even find any data points that you have not seen yet that would fit those rules. So when your model works really well for training data but very poorly for test data, then what we call is that your model is overfitting. So this is a problem, obviously, because ideally what you want is your model to work well for things that you don't know yet. So this is a prediction that all we care about. So how do we avoid overfitting? Cross-validation is a common technique to prevent overfitting. So here we're looking at an example of how to do fivefold cross-validation. And specifically, we're looking at only one iteration of cross-validation. So in cross-validation, we will divide the data into folds or parts. For example, in the first row here, you'll see that we divided the data into 5 parts or 5 folds. And we'll use 4 folds or 4 parts as the training data, which means we're going to use these 4 parts to train or to build our model to figure out its parameters. And once the model is built, then we evaluate it on the test set, which is the remaining part or remaining fold. And we'll get the accuracy for this fold. And we do the same thing for the second fold. So meaning we still use 4 parts as training data set, but here you notice that we shift the test set to the second part. And again, we get accuracy for this fold. And similarly, we move to a third fold, and so on. And after doing all 5 folds, then we have 5 accuracies. And what we do is we then take the average, then that becomes our cross-validation error. And of course, as we mentioned, this is only one iteration. So the accuracy that you get would depend on how you divide up the data. So that means ideally you want to do at least a few runs. The more runs, the better, and to compute the average. So in other words, the exact steps that you need to do is to divide your data into n parts. You use 1 part as a test set or whole set, and then you would train the data on the remaining n-1 parts, what we call the training set. And after that, we compute the test error on the test set, and we do step 1 to 4 n times, once for each of the n parts. And after that, we compute the average test error over all folds. So when doing cross-validation, we need to determine how many folds that we want to use. And the test set size, of course, depends on that number as well. So test set size equals the number of item n divided by the number of folds k. So k equals 10 is most common. So in other words, 10-fold cross-validation is most common. There's a variation of cross-validation called leave one out cross-validation. So it's a very fancy way to say essentially setting the test set size to 1. And this is a great way, essentially using every single data point to evaluate your model once. But as you imagine, this is pretty expensive because you exactly need to divide the data into n parts or to the training n times. So often, the recommended number to use is 10 because it's most common. And using other numbers, generally, we don't really recommend. For example, if you say if you use k equals 9, then people may say, oh, why not use k equals 10? So for that reason, it's good to stick with common numbers. In this video, we look at how to evaluate models, why overfitting would occur, and how to use cross-validation to prevent that from happening.